In this video, we're going to take a look at using the first and second derivative sign tests to determine some characteristics of a graph without even looking at the graph. So we're just going to, this example, again, if I'm going too fast, just pause the video anytime and to kind of take down some notes and catch up a little bit. But we're going to take this cubic function and we're going to answer a few questions about it without looking at the graph. One is, where is this function increasing and decreasing? Where is it going up or down? We're going to determine the coordinates of any local mins or maxes, local mins or local maxes. 3, we're going to identify intervals where the function is concave up or concave down. Concave up means it can, I guess, hold water, and concave down, which would mean it would be spilling water out of it if it were a cup. And then the last thing is to identify any coordinates of points of inflection. Those are places where the concavity changes sign from up to down, from negative to positive, or positive to negative. Alright, so we're going to use the first derivative test. So here's our first derivative. I've factored it so I can find where the zeros are, and those are going to occur at 3 and 7. So for our first derivative sign test, we're going to be looking at y prime. That's our first derivative. This is going to talk about characteristics of the original cubic function up here. So we have zeros at 3 and 7. So if the only two zeros are at 3 and 7, that means everywhere else, every other x value is going to, every other function value, y value, is either going to be positive or negative. So if I plug in 0, any number over here, I'm going to pick 0 because it's easiest. And I could plug it in here and see that it's positive. I think in the long run it's a little easier to plug it into the factored version. So positive, put a 0 here, I get negative. Put a 0 here, I get another negative. So a positive times a negative results in a positive. In between here, I'm going to pick a number like 4, 5, or 6. 4 is good. So if well, that's always positive. Put a 4 there, it's negative. Put a 4 there, it's positive. So positive, positive results in a negative. And then pick a number over here like 8 or 9 or anything else. 3, I'm going to put an 8 in, that's going to be positive. Put an 8 there, positive. So since the first derivative is identifying the slopes of our original function, we can tell the slopes are positive here, negative here, positive here. So positive slopes make this graph move up. Negative slopes are considering this graph moving down and up again. So to answer the first question, where is the function increasing? I'm going to say it's increasing from negative infinity up to 3, and then from 7 to infinity. So increasing from negative infinity to 3 in union with 7 to infinity. And then decreasing, this function is decreasing between 3 and 7. Okay, next question, coordinates of any local mins or maxes. And so what we're looking for here on the first derivative test is a sign change. Okay, and that's like, notice this one, a slope, and this is describing what our original function is. A positive slope, a 0 slope, and a negative slope. Notice what that considers here. That's a positive, 0, negative. That is a local max. On this one, negative slope, 0 slope, there's your horizontal tangent line, positive slope, there's your local min. Okay, so it says determine the coordinates of local mins and maxes. So our first local max is going to have a x coordinate of 3, and our local min is going to have a x coordinate of 7. And so if we plug 3, again, we're talking about the characteristics of our original function. So if we plug a 3 in here, we're going to get 81 for our y value. So 381. And if we plug a 7 into our function, our original function, we're going to get 49 for our y value here. So notice how these answers kind of look the same, but they mean two totally different things. And you just have to use them in context, because it says, where is the function increasing? Where, you have to understand that that's an interval. So this, not a point. This is an interval, a domain interval for the x value 3 to the x values of 7. And then here, it says coordinates. So in context, you know that this means we're talking about a point here. All right, next. Intervals of concavity and points of inflection. Well, both of those have to do with our second derivative. So we're taking a look here. Notice again I factored it and found the 0 for our second derivative. And I'm going to use the sign test for the second derivative. But remember, this is always talking about characteristics of the original function. So I'm going to place my 0 for our second derivative. That means everywhere else it's either positive or negative. I'm going to test a number over here. If I have a choice to use 0, I do it, and 0 is over here. So positive, put a 0 here, negative. Alright, negative value over there, that means it's going to be concave down. And then over here, 6, 7, 8, something like that, I'll use 6, positive, put a 6 there, positive. So this identifies that our original function is going to be concave down from negative infinity to 5 and concave up from 5 to infinity. So I'm going to mark that here. Concave down, we said, from negative infinity to 5, and concave up from 5 to infinity. Oops, that's an 8. 5 to infinity. And lastly, identify coordinates of any points of inflection. So we're going to be looking here for a point of inflection, but I just want you to make a little connection here. For a local min or max, we're looking for a sign change across the first derivative. For a point of inflection, we're looking for a sign change in the second derivative. So this went from negative to positive, that's a sign change. So there's going to be a point of inflection when x is 5, and when x is 5, if we plug that back up into the original equation here, we're going to get 65. Again, think of these answers in context. These are intervals. That's a point, the coordinates of a point. Okay, so we've identified all these things without even looking at a graph, but I just want you to see and make a little comparison here. Where all these things are. So notice, where is the function increasing? From negative infinity, so from way far left here, until it gets to 3. So notice right here, when x is 3, that leveled off right there. Okay? And notice we said it increases again from 7 to infinity. Look, this function is moving up from this x value of 7 to the right forever, to infinity. Okay? And notice where this function is decreasing. We said from the x value 3 to 7. So notice this function is moving down from the x values of 3 to 7. And we called a local max, had the coordinates 381. Notice that that's the point right here. The scales are different. Here's the x value of 3, and here's 80, and so we're a little bit above that 80 right there. And this point over here is 749. So there's our x value 7. Follow that across. There's 40 and 60, so we're right around 50 right there. Intervals where the function is concave up, concave down. We said concave down from negative infinity to 5. So right here at 5, there's that little transition. Notice it changed. Here's concave down. The water is spilling out of that cup. Here's concave up. The water is holding in that cup there. Okay, so there's that transition, and we determined that point, that where the concavity changed from down to up in this case was 565. So that is our point of inflection. And we can figure out all those things without even taking the time to graph it.